Okay, this is basically a book that came out called Ocean Prediction, Present Status and State of the Art, Current Capabilities and Emerging Frontiers in Ocean Forecasting. Obviously, very useful, and all this attention on climate change, climate predictions, climate projections, AI, ML, ocean is always there as well, a big part of the climate system, Earth system. And there are separate ocean prediction efforts that keep going on. Lots of applications, of course, a lot of demand, a lot of user base and stakeholders, etc. We will look at this book. Basically, I'll run through all the chapters. It's obviously a very long book with literally more than 1,000 references that are very useful as well. So it's not a classical textbook in that sense. It's more like chapters strung together with edited content that is very useful. Many entities are involved. Copernicus, State of the Planet, Mercator Ocean, another project that you hear a lot about, Ocean Prediction, UNESCO, UN Decade of Ocean Science, 4C Ocean Best Practice, and Ditto. I won't go into the details of what they are, but basically the book considers all these things: State of the Planet, Ocean Prediction. So there is an introduction, predicting at different scales, operational systems and applications around the globe, connecting with observations for improved forecasts, numerical modeling for predictive blue, green and white ocean. I think you know what that is, so let's leave that there. Building trust in forecasting, so aspects of how the users see the usefulness of these forecasts and how we can make them available and usable so that people do use them for making decisions, especially under the UN Decade of Ocean Science. We are worrying about exploiting the oceans sustainably and so on, which are also part of the Sustainable Development Goals as a whole. Representing air-sea land interactions for improved forecasts. So when you think about ocean forecast, we will touch on coupled forecasts a little bit, and also using AIML for forecasts, but basically most of the forecasts happen with ocean models that are forced from above, global or regional, and that involves fluxes. So how to represent air-sea land interactions when it's not a full coupled ocean climate model or Earth system model. Advanced modeling approaches for ocean forecasting. So obviously then you are thinking about system modeling, coupled ocean forecasts and so on. And finally, bridging ocean science and society. Okay, so end user applications and capacity development for, there are a lot of poor countries or developing countries that rely on the ocean for livelihoods like fishing, and they work on ships and etc. And they are often also, if you're on the coast, let's say in Africa, and the interior countries are going to depend on you to connect to the ocean for various socioeconomic activities, right? So I will, as I said, just be very brief, only show a few figures, and it's a nice book. You definitely want to read it. I just wanted to give an overview, and it most definitely will not be finished in one podcast. Maybe it'll take a couple, 3 more. So let's start. Ocean Prediction Decade Collaborative Center, DCC, connecting the world around ocean forecasting. What is it? Operational Ocean Forecasting Systems, OOFs, have proven to be immensely valuable today. Numerous successful and inspiring services are operating in various regions of the world and contributing to cutting-edge applications within the marine community. This success lays a strong foundation for building a global community around ocean forecasting. However, the development and enhancement of existing forecasting systems remain challenging due to the absence of best practices, standards, and community-endorsed architectures. So everybody is doing whatever is built locally, There is no global protocol as such. The Ocean Prediction Decade Collaborative Center (DCC) and its associated Decade actions aim to address these challenges by leveraging the UN Decade of Ocean Science for Sustainable Development, which is running now from 2021 to 2030, and the concept of digital twinning, which we'll touch on. I think you know what that is. We have discussed this elsewhere, where you make a complete computer model of the system you are dealing with. Could be regional ocean, could be some part of the open ocean, or could be the global ocean. And they are useful because you do experiments in the digital twin before you do something in the real world to explore the positive impacts, unintended consequences, and so on. So this paper introduces the Ocean Prediction DCC and outlines the forward-looking strategies to achieve these ambitious goals. The special issue introduced by this paper is part of this broader effort. So very nice collection, and you can look at these pages like the unoceanprediction.org, where this report is also available. Should I read all this? Not necessarily, but basically the UNDCC that we mentioned, is building on the UN Ocean Decade of Ocean Science, whatever it's called, right? So there are many entities involved, like the Intergovernmental Oceanographic Commission under the UNESCO, the Ocean Prediction Decade Collaborative Center, and of course there are very successful operational organizations like the Mercator Ocean International, which is now being given charge by the IOC UNESCO to coordinate the Ocean Prediction Decade Collaborative Center. Ocean Prediction Decade Collaborative Center, so I shouldn't separate decade. It's a collaborative center under Ocean Prediction Decade. Okay, there we go. The center acts as a global convener of multidisciplinary ocean prediction expertise, collaborating with intergovernmental programs such as the Global Ocean Observing Systems, Ocean Forecast Systems, Indian Ocean, and biogeochemistry programs, and so on. Okay, so lots of alphabets there. But basically the idea is to provide a collaborative backbone structure and a collective voice for the ocean prediction community, supporting the decade's implementation, focusing on creating a global inclusive forum, implementing capacity development and ocean literacy initiatives, promoting operational ocean forecasting systems, which is basically to support all the moves towards blue economy and ocean policy. Every country wants to do a blue economy, but that doesn't necessarily mean they are going to be sustainable. So some globally coordinated prediction effort can help make them sustainable and also give early warnings on marine heat waves or storms, etc. To develop a global technical and organizational structure centered on co-designing the systems, so making sure the data sharing and interoperability are part of the system, as well as digital twin, identifying needs and coordinating the development of new tools, standards, and best practices, and aligning decade actions with the objectives of ocean forecasting and fostering collaboration between decade initiatives and other relevant actors, because there are many efforts already underway from the World Climate Research Program, from IPCC, of course, and many other programs such as CLIVAR and so on. And also to support the Decade Coordination Unit ahead of the decade by collaborating with other decade collaborative centers and coordination efforts, ensuring alignment and monitoring of decade actions to secure their long-term legacy, and so on. Okay, Ocean Prediction Decade Collaboration Center Decade collaborate. I want to memorize it, but I keep on reading it and not remembering it. Okay, so here we go. Decade Collaborative Center, DCC. I'll just say DCC from now on. Okay. So how do you actually include that in the UN Decade ecosystem? 4C has the following overarching goals, so I won't read all of them because there are various sub basically when you implement such a global action, you set up units which look at different parts of the system to make sure that the entire thing gets implemented properly. So let's see 4C in this context. This has the following overarching goals: to improve the science, capacity, efficacy and use as well as impact of ocean prediction systems, to build a seamless ocean information value chain from observations to end users for economic and societal benefit. And these transformative goals aim to make the ocean prediction science more impactful and relevant. And there are others like Ocean Practice for the Decade program, Digital Twins of the Ocean Ditto, Digital Twins of the Ocean Ditto, which has been doing some very interesting things. Global Environment Monitoring System for the Ocean and Coasts, GEMS Ocean, Ocean Acidification Research for Sustainability, the NASA Sea Level Change Science Team, and Francis Priority Research Program, Ocean of Solutions. Why do I read those? Because you see that they are covering many aspects of the ocean science issues and the sustainability challenges as well as prediction needs, right? Ocean acidification is becoming more and more important because it's going to affect corals, fisheries and overall life and bottom of the food chain. Ocean Prediction Decade Collaborative Center collaborative structure has regional teams, the ocean forecasting co-designing team, and you see things like the Ocean Predicting DCC's virtuous loop towards the promotion of ocean forecasting. It has knowledge as a rubric, so ATOOPS under that. Architecture guide, so development of forecasting services, production, operation and upgrade, and integration and services, which also includes digital twins, that's the ocean prediction community. And jumping now ahead to, this was the introduction, jumping to the first chapter. They don't have chapter numbers, they just have topics written as parts of the book, so we will keep going in the order that it's listed in the table of contents we just saw. Okay, what are the core services? This is an introduction to global ocean forecasting. I will read all the abstracts of each of these sections and we'll look at some figures that I find are critical, but some topics are quite general, like how to validate the models and other things like how to calibrate things, etc., etc. Okay, operational oceanography can be considered the backbone of the blue economy. It offers solutions that can support multiple UN Sustainable Development Goals by promoting the sustainable use of ocean resources for economic growth, livelihoods and job creation. Given this strategic challenge, the community worldwide has started to develop science-based and user-oriented downstream services and applications that use ocean products as provided by forecasting systems as main input. This paper provides examples of stakeholder support tools offered by such applications and includes sea state awareness, oil spill forecasting, port services and fishing and aquaculture. There are many others. Also emphasized is the important role of ocean literacy and citizen science to increase awareness of and education about these critical topics. Snapshots of various applications in key world ocean regions within the framework of the Ocean Prediction Decade Collaborative Center are illustrated with emphasis given on their level of maturity. Fully operational examples can be used as inspiration for export to other areas. Of course, here is a quick figure, the ocean value chain as seen in this paper from 2022. Upstream data, of course, satellites, buoys, research vessels. Now you have lots of detailed observation systems, including volunteer observing systems, autonomous systems, and buoys now also include things like Argo. So you have Marine Corps service feeding information with immediate users getting direct quality controlled data as well as synthesized packages of data, and then there is other data sources that feed into it to create multiple downstream services, and then it feeds citizens, businesses and practitioners and policy makers, which are all end users, and each one is customized for the end user information need. Very general, but still kind of gives you a sense of how things are coordinated and how they are thought of. Okay. Another table here briefly, updates on the inventories as given in Alvarez paper 2022 and by oceanpredict.org, the website that we mentioned before, with focus on provided essential ocean variables, or EOVs. There is ECV, essential climate variables. So this is essential ocean variables. So I won't read everything, but here is India, for example. ESO INCOIS, the Earth System Science Organization, Indian National Center for Ocean Information Services, which runs globally at quarter-degree resolution with some regional Indian Ocean level models that are running at something like I think literally 1 kilometer, if I'm not mistaken. This is about 25 kilometers. So essential ocean variables, of course, are temperature, salinity, seas of a site, zonal and meridional velocity components, and mixed layer depth. I know that they also do tsunamis, waves, inundation, etc., tides, and so on. So 6-year average hourly fields for 5-day forecasts are given out. You can check out the website incois.gov.in. Okay, there are other examples. As you can see, the table is long because there are many spread out throughout the globe. Okay, second, ocean forecasting at the regional scale. What is the actual status? Operational ocean forecasting systems provide important information on physical and biogeochemical variables across global, regional, and coastal scales, obviously. Regional systems with higher resolution than global models capture small-scale processes like eddies and usually include tides, but lack detailed land-sea interactions essential for the coastal areas. Coastal areas are closely communicating with the land on fast time scales as well compared to the open ocean. These models, often nested within global systems, vary in spatial resolution from 1 to 20 kilometer and may include biogeochemical components, carbon cycle or fisheries, or some kind of a primary production which supplies the fisheries forecasts and so on. While regional systems focus on physical parameters such as sea surface height, temperature, salinity, and currents, only a few incorporate biogeochemical processes. The growing demand for biogeochemical data has prompted advancements, and more systems will include this component in the coming years for sure. This paper provides a preliminary overview of the current status of regional forecasting systems, discussing examples such as the Copernicus Marine Service from Ocean Predict, analyzing the offer in terms of covered regions resolution and catalogs of ocean variable products, EOVs. Again, a table showing many regions, so Australia, Blue Link, Brazil, Remo, Canada, China, Europe, India, we mentioned already, Japan, Republic of Korea, and the US. At least till now, US funding situation is evolving very dynamically and many things are getting affected, so we have to keep an eye on that. Next section now, solving coastal dynamics. Introduction to high resolution ocean forecasting services. That's the topic. I won't read all the details here, but basically we are talking about setting up close to the coast high resolution models and using things like high frequency radars and satellite missions like SWOT, Surface Water and Ocean Topography mission, which has high resolutions and is designed to capture ocean eddy dynamics and so on. It's also I think an altimeter, but it's arranged in a way that it is much, much, much higher resolution than the earlier satellite altimetry missions as well. Coastal models not only benefit from high resolution observations but also contribute to evolving observational systems, creating feedback loops that refine monitoring and prediction capabilities. Modeling strategies are also examined in this chapter, including downscaling and upscaling approaches and numerical challenges like implementing robust data assimilation schemes to refine estimations of coastal ocean states that are addressed in this chapter. Basically, the idea of data assimilation is that whenever you do forecasts, you have to initialize the model, especially ocean. Atmosphere moves very rapidly, so when you do weather forecast, you are initializing the atmosphere and the ocean is prescribed. But when you do ocean forecasts or coastal forecasts or regional ocean forecasts, you have to initialize the system, and that's called data assimilation, and we'll briefly look at the various approaches that exist as well. Okay, so the schematic representation of the coastal zone hazards like the harmful algal blooms, metocean and biogeochemical model variables and observations as well as applications are shown here. There are in situ observations and satellite, and there are also buoys, autonomous gliders and volunteer observing ships and so on. And there are of course models which are trying to do currents, sea level changes, oil spills, harmful algal blooms associated with eutrophication, where nutrient pollutions create harmful algal blooms, and you have high frequency radar, vertical land motion, subsidence also has to be accounted for net sea level issues, and you have agricultural runoff, impact from land use types, plastic nutrients, plastic pollution and nutrient pollution are everywhere now. Of course, waves, ocean acidification that we mentioned, cliff erosion, shoreline changes like coastal developments that change the interaction with the ocean, winds and heat and temperature, of course, and oceans are warming, sea levels are rising, acidification is happening, deoxygenation is happening as well. Okay. Circulation models in alphabetical order. I am not going to read all of them, but you probably heard of many of them like ADCIRC, COMPAS, NEMO, MPAS, MIT GCM, ROMS of course has been around for a long time, POMS, and so on. Okay, next section. Why am I being so brief? Because these are good topics and there are a lot of details, but I am just trying to give you a sense that the book covers all these topics with all these specific foci, and you need to go back and read the book or specific sections if this is of interest for you. Probably this will work well for part of a course on ocean predictions, but right now I'm just being very, very brief. Okay, a description of existing operational ocean forecasting services around the globe. Let's just look at the table. Global Ocean Forecasting Services on the Ocean Prediction Decade Collaborative Center Atlas. So you have GLOW MFC, Copernicus Marine, so that's part of the Mercator Ocean International. Essential variables, the models involved, the horizontal grid types and the resolution are given, so you can see also you have FIO Ocean, that's from China, FIO Ocean Forecasting System. There is another one, Norway's Nansen Environmental and Remote Sensing Center, Global Foam from the Met Office UK, INCOIS from India, MOVE JPN from the Meteorological Research Institute, that has to be Japan, and you have others like Real-Time Ocean Forecasting System, Hurricane Forecast Analysis, IMPI Brazil, INCOIS India, that's Wave Watch here, Global Ocean Forecasting System, Euro-Mediterranean, and Global ICE Ocean Prediction System from Canada, which obviously has lots of ice issues to worry about, Chinese Global Operational Oceanography Forecasting System, and Japan's Marine Earth Science and Technology institutions model. They are still running PALM. As you can see, each one is running different models. PALM is one of the older models, so for legacy reasons that may be still running there. Global Ocean Forecasting Services on the Ocean Prediction DCC Atlas. Yeah, that's the last one. Anyway, last page. Okay, so DKSS DMI. This is an example. This is basically looking at all the ocean basins and regions of interest collected in the storm surge section, for example. So it has contact information in case there is an emergency, main description, so year of start of operation 2001, so already almost 25 years long, and there are details like atmospheric forcing, etc. From the interactive website you can get all the details. Okay, so what are the regional and coastal models considered for? So they are relevant for a proposed set of downstream sectional applications and phenomenon of interest. So marine safety, these are scheduled, pre-operational and operational. So the blue are operational, so you can see marine safety, more than 30 models are operational. Oil spills, almost 25 or so. Water quality, more than about 15. Harmful algal blooms, again around 15. Storm surges, coastal eutrophication and hypoxia, shoreline and bathymetry changes, tracking those, modeling those, etc. Ocean acidification and tsunami. Tsunami warnings are given just based on monitoring seismic activities, but obviously not every earthquake creates a tsunami. So there are near real-time alerts given out by NOAA's office in various oceans, and other countries like India also maintains some sort of a tsunami warning system, which is also under INCOIS that we mentioned. Okay, so maybe it's a good time to stop here because this is probably already long enough. CPI use is high. Okay, this is more than 26 minutes, so I will stop here. Okay.